So good morning. I am Krishna Kumar from Krishna's classroom. We continue with our discussion on diagonalization, and today's theme would be the role of matrix representations in understanding the linear transformation. Now, last time we introduced what are called the eigenvalues and eigenvectors of a linear transformation. And we also found that if B equal to V1 Vn is an ordered basis such that TVI lambda IVI, then the matrix of T in terms of B is what would I write? Is diagonal. Now let us see. So the problem is essentially finding out VIs such that these VIs form a ordered basis for the vector space B. If we are successful in that, then we can immediately get the diagonalization. Okay. So these VIs should satisfy this particular equation, then you have a diagonalization. And we will go into the deeper meanings of diagonalization soon. Therefore, what one has is this following. So before that, we shall just examine the diagram that we are very fond of looking at in this regard. Now you see that how to compute these VIs. Now we can make use of the fact that the representation is diagonal with respect to VI. In that case, what happens? So let us take a scenario. Suppose P has if you call this matrix capital lambda, then we have lambda EI where EI is for I first we want to assert that The representation, see, in general the representation is an n by n matrix. Okay. So for any basis B, any ordered basis B, TB is an n by n matrix. Suppose there exists a diagonal matrix lambda related to it means there exists an invertible C such that C inverse C. Now for lambda, E1, E2, etc., En are eigenvalues, eigenvectors. We have that is EIs are the question that you ask is the following: is it possible to construct B, the ordered basis V1, V2, etc., Vn, such that let us explore this problem. Now go to the diagram that we are found of. E is a linear transformation which carries V to T. Now we know that from our assumption that there exists a diagonal matrix which is related to TB. Okay? So that's the assumption that we have made. Is it possible to find out the corresponding basis? This is the problem. So what one does is this. It shows that there is some basis without loss of generality. We will just designate this by B itself. Okay. Such that this is so we are assuming that we are rather assuming that B itself does the job of diagonalizing, because we have assumed that there exists some ordered basis. Without causing any confusion, we assume that we use the same notation B, or if you are very particular, you can use another notation. There's no harm in that. Or you can even use, I will just use that. Okay, let me keep this as it is. Right. Now, how are the ordered basis with respect to which T diagonalizes related to the eigenvectors of lambda? This is what we are going to investigate. Okay. So let me take Vi. Now let me take Vi. So if I take Vi, then what I am getting is Vi under this map. Right. Okay, let me just use this right. That Vi. See, if lambda EI equal to now what we are asking is, see, even E2 En is an ordered basis for n cross. Just see that. And phi is an isomorphism from V to Fn cross 1. So this is F. Okay. Therefore, phi inverse of E1, phi inverse of Vn is an ordered basis V. Why is it so? It's the pullback of an ordered basis for lambda. We just don't know what this phi is. Okay? That we will have to determine later. But what we know is, what we are assuming is that there is some diagonal representation which is equivalent to the any matrix representation of T in any basis. If so, we compute that, and then for that, for the diagonal matrix lambda, we see that this is a representation that comes out from from the choice of some ordered basis, or it's an isomorphism between V and Fn cross phi. Now you see that lambda ei we have here. Okay, and what is this lambda? Lambda is, okay, let us work out lambda. Lambda is in fact phi lambda is phi inverse T phi. So this is equal to first operate with phi inverse, then go to applying T and then this. Therefore, what we have is this: phi T inverse phi inverse of ei equal to lambda I, which implies, because phi is invertible, T inverse which is equal to lambda I. So suppose I put a parenthesis, then what happens? So here it is T, not T. Okay. So this is what you get. Okay. What does this mean? That is T of therefore, it follows that phi inverse of ei is an eigenvector of T belonging to eigenvalue lambda I. It is so for every lambda I. Or in other words, we see that since E1, E2, etc. En form an ordered basis, it follows that basis constructed out of ordered basis of n plus 1 by applying then one thing that you observe is that if there is a diagonal representation for T, then you can find or you can determine the ordered basis with respect to which T is taking that diagonal representation by simply taking out defining V1 equal to phi inverse of V1, V2 equal to phi inverse of V2, or in general we define Vi to be equal to, and this phi inverse of Ei we have already seen they are eigen vectors of T, which are eigenvectors of T. Therefore, the problem now reduces to simply searching for what are called eigenvectors of T. So, these phi inverse of Ei are eigenvectors of T. So, phi inverse of Ei are eigenvectors of T. Therefore, our task is now to find out the eigenvectors of T. It's not only that, you see, from this relation, we started with the diagonal form lambda 1, lambda 2, etc., lambda n. Therefore, lambda I, each lambda I is an eigenvalue of T. So, essentially, the problem reduces to finding the eigenvalues and eigenvectors of T. So that part is clear. So now the problem reduces to finding out how to find out then in this context we make some observations. Lambda and T has the same eigenvalues, and Ei is an eigenvector of lambda belonging to the eigenvalue lambda I. Then Vi, which is phi inverse of Ei, is an eigenvector of T belonging to the eigenvalue lambda. So we shall observe this is one observation, but that doesn't help us. Okay, because already we have got in a particular form. So we want this lambda to be lambda has to be the representative of T in some basis. In some basis. Okay. Now let us go one step forward. We make an observation that suppose B1 prime, B2 prime, B prime is an ordered basis, some ordered basis. Okay. This only says that if you know lambda, then of course you can get the expressions. But provided you should also know the phi is dependent on this Vi, which is almost working on a vicious circle. So that doesn't help us. Okay, so let us start. Make an observation. Let B and B prime be two ordered bases of B. Then let A denote not necessarily diagonal, these are the definitions of A and B. Now we want to make some observations. The observation is that see, there are certain invariants of A and B. B in the sense that there exists an invertibles C and n by n matrix such that B equal to AC. Now we immediately observe certain facts. What are the facts? You can immediately show that determinant of B equal to determinant of C inverse AC. And you know that the determinant of the product of two matrices is again the product of the determinant. So we make use of that. So this is equal to determinant of C inverse into determinant of A into determinant of C. But determinant of C inverse equal to 1 by determinant of C. Now this is because determinant of C is not equal to 0. C being invertible. Okay. Therefore, both B and A have the same determinants. Okay. Now we have made some observation. What are the eigenvalues and eigenvectors of A? See, A is a map from F n cross 1 to linear. That is, A belongs to the linear map. Now lambda is an eigenvalue of A if invertible is non-invertible, or what you call singular, and this, which is if and only if determinant of lambda I minus A is different from 0, equal to 0, sorry. So determinant of lambda I minus A is equal to 0. Okay. One more thing that you observe here is that if B is another representation of A, then if B is related to determinant of lambda I minus A equal to 0 if and only if determinant of where therefore we see one thing. Therefore we observe that irrespective of what ordered basis you use, you get a representative matrix. Therefore, irrespective of the choice of the property that this for all ordered bases, this is true. Okay. Now what do we do? What we want to do is, we want to diagonalize, find a diagonal matrix which is related to any one of these representations. To get a representative matrix of T, there is no problem, no constraints at all. You just start with any ordered basis, then you can get it. Now this is to get a representative matrix. We can start with any ordered basis of B and get the corresponding matrix representation. So our strategy is to choose a very convenient ordered basis for V without ever bothering about what T is, and then get the matrix representation of T with respect to that basis. It's an n by n matrix. Now what is the next step? The next step is to construct a diagonal matrix lambda which is related to this matrix. Okay, so our strategy is start with any ordered basis of V and then compute the corresponding Now the question that you ask is this: do you have a diagonal matrix which is equivalent to this representative matrix? So the next question is this: does there exist that we have constructed? This is the question that you have. Or simply saying, can you diagonalize that matrix? Okay. So let us see how this can be done possibly. So our strategy is this: we have P belonging to LV, then P choose some ordered basis B, then you have B. So now you are already in Now you are asking, can you diagonalize? Does there exist a lambda This is what we are asking. So the problem reduces now to diagonalizing the matrix representation of T with respect to B. So in short, we look at a larger problem. Given a n by n, for a moment we will leave this V and T. We will ask a larger question. Given One more question now. Does there exist, given A, does there exist a diagonal form of this, or a diagonal lambda which is what is called related to the given matrix? Okay. Now here we make use of one fact. Now we know that both lambda and A eigenvalues, if they are related. Okay? They have the same eigenvalues. Therefore, the problem reduces to find. So, the problem is now how to find whenever they exist. This is the question now. And then we can link up everything. Okay. So how have we started? We started with a t belonging to a v. Okay. We chose some convenient ordered basis for v with respect to which t has a matrix representation. We know how to compute it. So now the matrix representation of t with respect to the ordered basis that we have started with is known. Okay. Now the question that you are asking is this diagonalizable? Okay. If it is diagonalizable, then how do you find out the diagonal form? Okay. This reduces to establishing whether you have got enough eigenvalues for A so that you can get the diagonal form with the eigenvalues sitting along the diagonal and all other entries 0. That's the structure of lambda. Okay, so how to find out the eigenvalues? See, we know that lambda is an eigenvalue of A if implies there exists a vector x belonging to such that Ax equal to lambda x, and this we know is equivalent to A minus lambda I, lambda I minus A is That is because we are looking at this equation, we are asking whether this has a non-trivial solution, because I said yesterday that this has always a trivial solution. So we are not interested in that at all. For no matter what lambda is, this equation has the zero solution. So we are interested in asking whether there are some values of lambda for which this equation has a non-trivial solution. Or in other words, find values of lambda for which lambda I minus a is singular. That is if and only if you know that this is non-invertible if and only if determinant of equal to 0. And what is this? This is a polynomial with of degree, but determinant of is a polynomial f lambda with coefficients in where f belongs to P and f. That means it is a polynomial of degree n over the field f. Quite easy to work it out. Okay. You have to compute the determinant of lambda I minus a. Now, if you want explicitly, you can do this. If a is equal to then determinant of this is computation of the determinant of this. From this it is clear that this is equal to and this f lambda is called the characteristic polynomial of A. Okay. So f lambda is of the form something like f lambda is equal to some lambda to the power n plus n. This is this. This is the form where AIs belong to so the coefficients are all in F. Now what do we want to do? We want to find out, essentially we want to find out the values of lambda for which F lambda is equal to 0. So the eigenvalues are necessarily the zeros of the polynomial lambda. So what we do is we compute the eigenvalues by finding out the zeros of this polynomial. Okay. So the problem now reduces to finding out the zeros of polynomials. It's a sort of dead end. Dead end in the sense that it's not an easy task to find out the zeros of a given polynomial. There is no general method except when the degree of the polynomial is less than or equal to 4. Beyond that, there is no general method. But in some cases, possibly if you can reduce the if you can factorize in some way or other and reduce it to polynomial of lower degree than 5, then you can try to find out the roots of those factors, each of which is a polynomial of degree less than 5, okay, by some general methods. But so in general it is not a very easy task. And that leads us to the polynomial. So that takes us we can use all the tools available there to tackle this problem. Okay. But even if you are not able to compute eigenvalues or the zeros of the polynomial, still you can ask the question, do you know that they do exist? Okay. It's a one thing to compute something, another thing to prove that there exists a polynomial. This is quite often in mathematics. There are many problems for which we may not be able to explicitly compute the solution. However, we may be able to say that there exists a solution. It's quite often you see these kind of problems. So given a polynomial, of degree zero of the polynomial. How many such? If yes, that's the last priority question, because you know that it's a formidable task. Okay. So this is the problem reduces to this stage. Okay. So it is finding the zeros. So what have we reached? We have reached with the D. We used an ordered basis B to get the characteristic polynomial. You know that this is an invariant, so it does not depend on B. For any choice of B, whatever matrix you get, that will have the same determinant. And then zeros of so this is where we reach. Okay. Now you know that at this stage I think we can make an addition. If f lambda is a okay. This is the characteristic polynomial. polynomial of B prime any ordered basis B prime of P. B is an ordered basis. This is because you have determinant of identity of identity matrix. So this is I equal to n by n identity matrix. This is what you. This is the sentence. So we have come up to the problem of finding the what are called the zeros of the polynomial of degree n. Now suppose you get now what we can say is that if f is okay, one case where you can say that the all the eigenvalues do exist or all the zeros of P exists in F is when F is algebraically closed. If F is algebraically closed, then all the roots of the polynomial that is the same as what are called the zeros of the polynomial. Exists this is what you mean by algebraically closed polynomial. It's a general theorem. It's one of the big theorems or the fundamental theorem of algebra. So this is in fact for example, Q is not algebraically closed, R is not algebraically closed, but C is algebraically closed. Okay? So if you take a polynomial of any degree with complex coefficients, then all the roots of the polynomial lie in C itself. But you cannot make the same statement about the polynomials with the real coefficients with the question asked whether the zeros exist in R, or the same question asked with Q as the associated field. Okay? For example, if you take the polynomial, suppose f lambda is equal to lambda square plus 1, and then search for the zeros of this polynomial. Has no zeros in R, whereas has I and minus I This is a very simple example to highlight the problem. Okay. So you are comfortable if you are working with an algebraically closed field. However, there may be situations where the all the roots may lie in a given field itself, whether it is algebraically closed or not. For example, if f lambda is equal to then this is equal to whole square, and f lambda equal to 0 implies with multiplicity two. That means you see that there are situations where the field may not be algebraically closed, because you can even ask the same question in Q, because this is a polynomial of degree 2 with coefficients in Q. Okay? Then you see that all the roots are in Q itself, although Q is not algebraically closed, or R is not algebraically closed. Okay? So there are situations where all the roots are, see, this cannot have more than 2 roots. I mean, that's also something that comes from the fundamental theorem of algebra. Can have at most as many roots as the degree of the polynomial. Okay? So that is something that we get. And if you know the roots, you can filter them out or factor them out. Okay? So if we know that there are k roots, each of multiplicity, say n1, n2, etc., and then you can factor it out as follows. See, f lambda can be written as okay. If F can be linear polynomials. Then in that case you will get n, which is a degree of the polynomial. Okay, but this is not necessarily always true. For instance, you have seen this example where this cannot be factored out. No, because there are no roots available. Okay. Sometimes what happens is if your f lambda happens to be suppose this is the situation. This has polynomial has three roots. In C, but has one root namely the other two roots are complex roots which are not in R. Therefore, we cannot say anything about the existence of roots unless the field is algebraically closed. Only if the field is algebraically closed, then you can say that it can be written out as a product of linear factors. So that much we recall for the time being from our knowledge of polynomials and their roots. Okay. Right? So we shall put down some of the results that we have covered in this discussion. One of the theorems is that, so let us write down some of the results. That we have come across or used during this discussion. Suppose T belongs to our basic assumption holds and lambda belongs to the assumption. Then one, lambda is an eigenvalue of if and only if definition before that, because we have seen here you see in this statement that determinant of lambda I minus t is appeared. But you know what exactly? Okay, so let me just take it. After I define it. See. Now determinant of determinant of lambda I minus t is defined as determinant of lambda I minus the matrix of lambda I minus t b, which is equal to determinant of abuse-of notation. So this is an n by n matrix minus. So in this line, so this is now this is justified because of the following. Let us we prove that the determinant of if B and B prime are two ordered bases, B then B prime and this is easy to do. So let us do a quick proof of that. You know that the matrix representation of, suppose an ordered basis of B, then the ordered basis of B plus plus so we make use of this. Now you know that the ordered basis, if any ordered basis B, the representation is I B. for any ordered basis V. Therefore, we can now immediately write what it is. That is the this is related to that is because P of U and the earlier property. Okay, so this is the n by n identity matrix that you have. Okay, therefore, now you see that the determinant of is the same as P prime, because you have the relation that and we have seen that the determinant of this product is actually determinant of C inverse into determinant of this into determinant of C, and you know that determinant of C inverse is equal to 1 by determinant of C. So now you are just working with the scalars which commute each other. Therefore, I can cancel this determinant of C with the determinant of 1 by determinant of C. Determinant of C is not equal to 0. Therefore, you see that the determinant is an invariant over the related matrices. That's what we have used. And that is the reason why we have written determinant of lambda minus I. So we are justified in writing determinant of lambda minus I. Therefore, this is well defined. Okay. Now we also put the third part of the theorem is, therefore, the following statements are met. T belong to LV and lambda belongs to F. The following statements are equivalent. The third statement is that it's quite straightforward to prove, so I just leave it to you to work out the proof. Assume that lambda is an eigenvalue of T, which means this equation, that is lambda I minus T of has an non-trivial solution. This is what you mean by lambda is an eigenvalue. What does this mean? Suppose lambda is an eigenvalue, then this is a non-trivial solution, which in turn implies that lambda I minus T is a linear transformation on V, which is not 1-to-1, which implies lambda I minus T is singular. Okay? Now, if lambda I minus T is singular, then one can immediately prove that the determinant of lambda I minus T is equal to 0. All that you do is you go to the matrices. Okay? So you will get that this is singular. And for matrices, you don't know, you are comfortable with matrices. This you know, this means that the determinant of is equal to 0. And this is exactly what we call, that is from our definition of determinant of T, we have this is equal to determinant of C. Now once again go from here. If determinant of T lambda I minus T is 0, what does it mean? There exists a certain x such that x not equal to 0 such that this is equal to 2. That means x is an eigenvector of TB with reference to this vertex belonging to the eigenvalue lambda. Okay? What does it mean? It means if you pull back to this using the basis. So with the choice of basis, now you see that with the pullback of x to v, because this is what we have. This is v, this is your this is close to lambda x. Therefore, take that x and pull it back. So, if this map is fine, then you take phi inverse of x, which is equal to some v belonging to v. Then you have v of v equal to v of this is equal to what? Lambda of phi inverse of x. And phi inverse of x is not equal to 0 because of this relation. What did you have? You had d TB is equal to phi inverse of so we are using this. So this is one of the results that you can prove. The second result that we have proved in the process is the following. We have also proved that the determinant of because these two can be connected using, because these two are B prime, and which follows from the fact that okay. So that's the result that you are getting. So now where do we stand? We stand with finding out if it exists the zeros of the polynomial. That is the problem. In fact, we have to, given t, we have to find out the characteristic polynomial f and find out the roots of the polynomial. So this is where we stand. given T, we have to find the characteristic polynomial T which is essentially determinant of this result, because it is invariant under a change of basis. And once you get the roots of lambda, you can find the they turn out to be what are called the eigenvalues of T, and you have to find the corresponding eigenvectors. This is the problem. I think we'll stop here. Take it up further tomorrow. Thank you very much.